For this presentation this evening by Canadian Prairies Group of Chartered Engineers. My name is Tachi Murthy. I'm the mechanical rep for CPCGE. I have known Jimmy for a very long time, I think, through cricket. We started playing cricket together in the mid-'80s, I believe, Jimmy.
Correct.
And, there's Bala there and a few others who will be joining us from the cricket team. Jimmy is going to talk to us about properties of sulfur, contaminated sulfur reclamation. To tell a little bit about Jimmy, Jimmy had his Bachelor of Science education in chemical engineering in University of Madras, Chennai. Then he has also got a master's in chemical engineering from Stanford University. Then he's also got a PhD in chemical engineering at the State University of Buffalo. He's an experienced professional in the sulfur industry for over 35 years. He has served in several diverse disciplines from R&D and process engineering to operations, project, and engineering management. Without taking too much time, I think there are lots of things in his bio you can read. Just a little bit of housekeeping as a people. At the end of this session, Jimmy will be happy to answer your questions, but he would prefer not to answer questions during the presentation unless something is totally wrong. He want to say that no, it's wrong. Otherwise, through the chat, send the questions as you think of them. Then Jimmy will get to that, go to all the questions as much as possible at the end of the presentation. And here is Jimmy.
Thank you, Tachi, for your kind words. It's been my privilege to have been asked to make this presentation on some aspects of the sulfur industry, particularly remelting sulfur blocks. One thing I just noticed on the title block, made a mistake in the spelling. It should be review of relevant properties, sulfur properties. And I was sort of conflicted between using for or and I forgot I left the D in there. So that is correct. For contaminated solid reclamation, just an apology. Okay. Anyway, I'm basically retired, though I still have a couple of projects that I'm finishing up on. But if you guys need any additional information on sulfur or in all the sulfur pieces, they're all downstream of the Klaus process, which produces the liquid sulfur. You've got my email here. Always welcome to answer questions, queries, anything like that. So let's get going. So this is the content highlights. The first two parts are the properties of sulfur and the molecular phase changes over this temperature range. You wonder why I'm talking about that, but those are absolutely essential to understand why sulfur behaves the way it does. It has very unique properties, and most producers don't like to deal with sulfur. That's why small companies or sulfur specialists have had a good career doing this. Then I also want to touch on the sources of sulfur and the transportation of liquid and solid sulfur, the environmental issues encountered, as well as the processes to deal with these issues. The gut of this presentation is going to be in the need for melting solid sulfur, the issues with contaminated sulfur, pure sulfur, and the processes that are available, and then finally conclusions. So let's move on to the sulfur properties. So I've just put in a table form some properties of interest that of relevance. Let me put it this way. Let's see the first one, which it melts in a range of temperatures. And again, why does it melt in a range of temperature? We'll explain it in the next slide as we go along. The flash point of liquid sulfur, the vapors, is 168 to 187. If you know what a flash point is, it's the lowest temperature at which, if you have a source of ignition, the vapors can flash off. The other property which is of interest is the viscosity change. Now I'm talking of pure sulfur. The viscosity generally in the region from about 159 down to 120, it behaves like a normal liquid. The viscosity drops as the temperature increases. But at 159 degrees, the viscosity spikes. And again, the liquid almost becomes like molasses, very thick as molasses. And we'll discuss that in the next slide, why this happens. Again, now these are, then you have auto ignition potential of dust cloud at 190 degrees. The lower explosive limit of dust clouds is 35 to 1400 grams per meter cubed. And I've just talked about the hazards. The other two very interesting properties of sulfur are its very low electrical conductivity and its very low thermal conductivity. The implications of the electrical conductivity being low for both liquid and solid is it's very prone to static discharge. And this is one thing that a lot of people who deal with sulfur or are just starting to deal with sulfur don't realize. Very prone to static discharge. I've in dry climates, we had a outdoor stockpile at Crossfield, stored farm product outside, and I'd walk up at night on the stockpile, I could see sparks coming off my boots. Same thing with liquids. The thermal conductivity also is very low. It's a very good heat insulator. So if you have a tank of liquid sulfur and the heating is removed, first you form a crust on the outside, and that sort of keeps it insulated, and the freezing happens very, very slow towards the middle. So you can keep liquid sulfur for a long period of time. And I've heard of stories where they poured blocks and big blocks, and 15 years later, as they've been trying to reclaim the box, excavate the blocks, they've come across molten sulfur. And where this is important is when you're pouring you're pouring sulfur to block, you have to only pour it in very thin layers. If you start pouring it in very thick layers, you could very well have molten sulfur underneath. And this has happened where the operators who are on top of the block trying to squeegee the sulfur around have sunk into the sulfur, into molten sulfur. Liquid sulfur also is very reactive with hydrocarbons, typically organic hydrocarbons, and also with H2S. With hydrocarbons, you have the formation of a compound called carcel, which is also a short form of carbon sulfur. And these are very tenacious compounds that very hard when they takes a little while to mature, but when they mature, you form a thick, hard mass that will coat heating coils, will collect at the bottoms of pits and tanks, and need to be cleaned out. H2S, of course, if you have H2S in the sulfur, it is present both as a physical H2S as well as a polymeric form, which is chemically bound. And that's stable. So that's where you can have H2S and sulfur for a long time unless you try and degas it. And another important property of sulfur is it shrinks. When you solidify it from the liquid, at the melting point, you get about a 7% shrinkage. And then it goes through a crystallographic transition around 95 degrees, where the crystal structure changes and it shrinks a further 6%. The implication of this again comes in, and if you don't understand that the shrink, it behaves exactly the opposite of water. So if, for example, and this has happened in a long pipeline in the Middle East that was electrically traced, where they lost power and the sulfur solidified in the pipeline, and they turned the power back on. And with electrical tracing, you don't get uniform heating. So there were plugs of solid sulfur while the middle part was liquid. And the liquid started expanding and literally ruptured the pipeline. So these are the type of things I want to bring to your attention that you have to understand before you proceed. So to understand why it behaves so funny, here is a viscosity chart of sulfur. And as you can see in the region from 119 down to 160, sorry, it drops from around 12 centipoise to something like 6 or 7 centipoise. That's a normal behavior as you heat a liquid. But then right at 160, it skyrockets up. The reason this thing is divided into is just because of the strange behavior. It goes up to 190 and then starts dropping. Why? Let me get the next slide. Okay, here we go. I apologize, it might be a little small for some of you guys, but basically look at the L region. L is liquid and S is solid. Whoops, went too far. So what happens with sulfur at the higher temperatures? Is the stable sulfur molecule is that drawing that was on the title page. It's a cycloocta S8 molecule, but you have S7. You have sulfur is an element which has several allotropic forms which are stable, which is your S2, S4, S6, S7. Now these molecules break up, and you have free radicals at either end that join up. This happens at the high temperatures at about 160 degrees or so, above 160. And then you start forming polymers, long chain polymers. This is why your viscosity goes up, because these monomers are formed, these polymers are formed. And also this is important, as you start cooling, it's completely reversible. As you drop the temperature, it reverses back to the cyclooctasulfur form. But this happens slowly. So the thermal history of sulfur, depending on how you cool it, if you cool it fast, you can trap some of the so-called polymeric or amorphous sulfur in the liquid, which reverts back to the stable form very slowly and provides strength. But it will revert back to the cyclooctasulfur, and that's why you've heard terms of curing sulfur, aging sulfur. Why aged sulfur is so weak? Because finally the polymers act as reinforcing agents for the sulfur if they are present. And once they vanish, then the sulfur loses its strength, goes back to the normal cyclooctasulfur molecule. So at 119 degrees, that's the freezing point, the liquid converts to the monoclinic form of sulfur, which is stable in that temperature range between 95 and 119. And that's when the volume shrinks by 7%, the crystal structure. Then at 95 degrees, there's a further transition into an orthorhombic structure. And it again shrinks by another 6%. And again, these things don't happen right away. They take time, and they're all exothermic reactions. So as you're cooling the sulfur, it's solidifying the sulfur. It's giving off heat. It's giving off heat at 119 and at 95 degrees. And all these processes are slow. That's why when you form sulfur, sometimes the temperature rises over time, and this creates issues like caking. And then there's also a non-classical glass transition temperature at 78 degrees, which was found by thermomechanical means. And I'm not familiar with what are the implications of that. It's just that it's one of those things that are found. So this is the reason why I wanted to talk about the so-called phase transitions of elemental sulfur, and that'll understand why it can behave differently depending on the thermal history. For example, if you take hot liquid sulfur, very hot liquid sulfur, and you toss it in dry ice, you can literally bounce it like a ball. And then you wait for a few minutes and it becomes hard and it shatters. Okay, so I'll briefly touch on sulfur sources. Back in the day, one of the main sources of sulfur was from mining, from pyrites, volcanic deposits. There were huge volcanic deposits in Sicily, deposits in Poland. They're still mining in Poland, as well as in the southwestern US. And they had processed to recover this mine sulfur. usually contains impurities, like I've said, like hydrocarbons, H2S, trace quantities of elements like arsenic, selenium, tellurium. That's when one of the product specifications for sulfur is it cannot contain so much of arsenic, selenium, tellurium. But in reality now, with most of the sulfur coming from natural gas, none of those are there. The main production these days now is actually involuntary production from environmental constraints. When you have when you process natural gas, you have to remove the H2S content to convert it to sales gas. And in the process of converting that H2S of removing the H2S, typically by scrubbing with amine solutions, and then you concentrate the H2S and convert it to sulfur by what is known as the Klaus process. The sulfur that comes out of this process is very, very pure, 99.9%. And this is now the largest production of sulfur in the world. It's one of the few commodities that is shipped at this purity in large quantities. Say sulfur can be shipped in 75,000, Panamax ships 75,000 tonners at this purity. It's one of the few compounds that, few elements or few commodities that are transported at this concentration. In reality, I consider it the sewage of the gas industry because it's produced involuntarily and the gas producers have to get rid of it somehow. So this is basically the sulfur production from Tucson natural gas, crude oil, tar sands. Basically, you try to remove the H2S or sulfur out of it by the Klaus process. I don't want to spend too much time on this. And how do you transport sulfur? Liquid sulfur, commonly for long distances on land, you transport it in rail cars. These rail cars have steam coils on the side so that you can steam them out when they reach the destination. Depending on how long the journey is, you might have to steam for a longer period. If it's a short haul, like trucking, generally they don't steam it. In barges also, they use it in barges for short trips, short ocean trips. But all liquid transport mechanisms have to be outfitted with coils, some sort of steam heating mechanisms, typically steam, also thermal oil, also electrical heating systems. Of course, it's the same thing. It's transported in pipelines. You have to have heating there. Solid sulfur. Now, if you have to transport it internationally, long voyages, then you have to transport it as solid. In the old days, they used to transport it as crushed bulk. They used to just pour the sulfur onto the ground and then crush it up and ship it. But this creates a lot of dust, and there have been some explosions. Actually, there was a famous explosion in the hold of a ship. And then the industry decided to go into safer forms of transportation. So you have prills, granules, rotiform, which is almost like a Smartie for international transport in high tonnage quantities. It's also transported by rail and as bag product. But I've seen crushed bulk sulfur being transported, still used, but what they do is they fill it up in containers and close the containers so you have no issues with dust, or you transport it in bags. Environmental issues around liquid sulfur mainly deal with emissions from the storage and handling processes. It's typically the off gases like hydrogen sulfide, sulfur dioxide, and sulfur vapors. Now, anytime liquid sulfur is exposed to air, you will have trace quantities of sulfur dioxide, whether you like it or not. And the longer the liquid is exposed there, the more the SO2 that is formed. So it's trace quantities, but it's there. H2S comes from the Klaus process. Typically, if it's not degassed, it can contain anywhere from 150 to 200 plus ppm H2S in the liquid. And it slowly evolves into the headspace. The dissolved component slowly evolves into the headspace, and you can have some issues there if the headspace is closed. For example, in rail cars. Unfortunately, we don't have any regulations for H2S content, liquid sulfur content in North America. It's only left to the individual companies to enforce some guidelines. Everywhere else in the world, there are regulations that you cannot ship sulfur over 10 ppm H2S concentration. Now, a few companies have adopted that guideline, but many haven't. And we transport undegassed sulfur in Alberta and in North America, which is not a very safe thing. People have died trying to open the hatch of rail cars and unloading rail cars. So much for that. On the liquid side, on the solid side, with these blocks, the main issue is the acidification of the soil, as well as uh, fugitive dust emissions when you start to reclaim the block by using excavators. And the biggest issue is acid formation. When you have sulphur-loving microbes, which are ever present, thiobacillus oxidans, they call it, ever present in the environment, and under the right conditions, say 10 to 50 degrees moisture, which happens in summer here, you have acid formation, and the runoff is quite acidic. So you have to line the edges of the block with a geotextile, collect the runoff, treat the runoff, and that process is quite expensive. I've heard figures of something like almost $1 a year per ton of sulfur in the block. So not cheap. So how do you deal with some of these off gases? Your liquid sulfur emissions like I said, of the sulfur, typically of the H2S more than anything else, if they are higher than what the regulations permit, then you have to deal with it by scrubbing. You can use chemical scavengers like caustic, or regenerable with redox systems. And sometimes solid systems also have been used, like iron oxide or aluminum. Typically, if they are high, you incinerate the off gases, convert them to SO2. SO2 limits are a lot more loose than H2S. Solid sulfur, the issue there is acidic. When you try to remelt it, you could have issues with your materials, corrosion. So you will have to neutralize it by blending with lime before you melt it, or as you're melting it. And if it's highly contaminated, your only option is sending it to a hazardous landfill. Anything over 4% sulfur needs to go to a hazardous landfill. Now Alberta has changed it a little bit, where they have specific landfills where they've lined. Before, you had to blend the lime with the sulfur, with the hazardous sulfur, to put it into the landfill. Now they've lined these pits with limestone, and you can dump in sulfur without having to blend. And of course, one company here called BioCycle is buying contaminated sulfur, which has a contaminated sulfur with a very significant soil component, like typically the bottom of base pads, and they blend it with compost that they buy from the city and sell it as fertilizer. So that's one option. Okay, now we get into the guts of the presentation. So the most significant use, again, of sulfur all over the world, I haven't discussed the uses, the main uses. The main use is producing sulfuric acid. Sulfuric acid then is used either as a precursor to sulfatic fertilizers, or mainly to extract phosphate from phos rock. So you have these large phos rock deposits in Morocco, in the southwest US. Many sulfuric acid plants, well, basically the fertilizer plants, they need the phosphatic fertilizers. So you need these sulfuric acid plants require liquid sulfur. What they do is they burn the liquid sulfur in burners, convert it to SO2, SO3, and all that, and create the sulfuric acid. That's a process that it's been around for many years. So they receive, if the acid plant is close to the sulfur producer, you can get it as liquid, no issues. But most commonly, these fertilizer plants, these sulfuric acid plants, are far away. So they are sent as solid, transported as solid, and melted there. So there's your need for melting. Now, sulfur prices are very cyclic. They have been as low as $20 a ton in the middle 90s, which caused a lot of sulfur farming plants to shut down and a lot of sulfur producers pour to block because it's not cheap to move sulfur. The transportation costs are quite significant. Up north here, there is a fairly significant producer. I'm not going to name names who has just decided to pour to block, and it is one of the largest blocks in the world. There were three major blocks in the world in the 80s, in the 90s. Two of them have been reclaimed. One is here in Alberta, which they started reclaiming back in I think the 90s, and one in Kazakhstan, which has been completely reclaimed. There's still one left in Alberta that they're slowly planning to reclaim. Now, the next question is, why do you pour to block and why don't you farm it and store it? The problem with farming and storing it is it requires a larger footprint, and you can have greater acid formation. You have more moisture getting trapped in the interstitial spaces, and you have a lot of formation of fines over a period of time. So these sulfur fines can actually be like concrete at the bottom of the pile. So it's typically poured into blocks. And like I said, they're expensive to maintain because of the cost of treating the runoff water. And again, like I said, sulfur prices though have spiked. I'm not a marketing guy, so I can't, I don't know the reasons for all this, but typically prices, the more common prices are about $70 to $90 a ton. And that's what they were early 2020. Now they spiked to $265 a ton. And I've seen them actually go up to $770 a ton. That's when producers need to use the window and start melting what blocks they have. And I've just mentioned something about how much thermal energy need to require 1,000 tons a day. And again, this is all pure sulfur. Anytime you have moisture in the sulfur, your steam requirements jump tremendously, and we'll discuss that in the next page. Okay, here's a picture of a block in northern Alberta. The pouring tars have been removed because this block has been sitting quite some time, and this is part of several other blocks of this company. If you notice, the sides of the block are stepped, and that's more for safety reasons. If for example, there's any crumbling at the top, at least the workers are protected down below. And you can see the size of the blocks. The picture is taken from a helicopter, but this is a massive block, probably about 1 million tons. And like I mentioned, these blocks have to be poured in very thin layers. So you have a pouring tar in the middle with a swivel arm that pours sulfur, and then the operators sort of move it along to the edges. And the edges, you have interlocking blocks, aluminum blocks that are placed all along, act as a barricade. And as the sulfur forms and solidifies, you lift the blocks up into the next level and next level. Okay, here are the issues that one has to be very careful of. I have experienced pretty much every one of these. Most companies, they see a block, they see sulfur, oh yes, we can remelt it, let's go for it, and wind up with a lot of issues. First thing, moisture. Moisture, now sulfur is hydrophobic, but you can have moisture from rain, snow, things like that. And for example, if you use a wet drilling process where your liquid sulfur droplets are solidified in water, you can have water trapped in there, about any 3 to 4% moisture. And then in the transportation of solid sulfur, you can pick up moisture. So this affects melting rates significantly. For every percent of moisture, typically you design a remelt for about 2 to 3% moisture. But every time you go a percent over it, you require 15 to 20% more steam. And I've seen this. If you don't have the steam, then the only way you can get by is by dropping your throughput. I've seen throughputs drop from 750 tons a day down to 400 tons a day or 350 tons a day when there was excess moisture, when there was rain, stuff like that. The other problem with moisture is you can have foaming. When you start melting, you have extreme foaming, and if you do not design with enough headboard above, that foaming can spill over your melting process. And this makes it very difficult because now you need level detection to make sure you're operating at the right levels, and you have to make sure you've got the right instrumentation for it. Like I said, open area wave guided radar level gauges. So in the sulfur service, you require special instrumentation in many respects, and I'll come to that later on. And of course, we've been talking about acidity. You have two ways of building acidity. One is sulfur itself, solid sulfur itself slowly oxidizes to sulfur dioxide, and you can have moisture around, which forms sulphurous acid. It's extremely slow, but the quicker one is the microbiological oxidation by the microbe Thiobacillus oxidans that is always present. Creates most of the acidity from outdoor stockpiles, especially when these piles are left for a long time, you can expect them to be acidic. Uh, the only issue there is you control it by appropriate metallurgy of your remelting equipment or using lime addition. The only issue with lime addition is now you'll have byproduct formed, which is your calcium sulfate or gypsum, and you'll have to find a way to filter it out of the system. H2S. This is another problem. If you have H2S in the sulfur and you start melting, as it's released, melting will release H2S. You can release anywhere from 20 to 70% of the H2S, depending on the conditions during melting. And a lot of the times the melting, you require agitation. So that will also cause a release of H2S. So typically all melting processes, if you have H2S, you have to provide sweep air, you have to vent it, and you have to make sure you meet emission standards. Typically the sweep air with H2S in most cases is incinerated. But in terminals or near cities where the emission requirements are very tough, you will have to go with the scrubbing system. You can't incinerate. And there are also corrosion issues that are faced depending on the metallurgy you use, of course. That's what I've been talking about, metallurgy. You have an electrochemical corrosion process when wet sulfur contacts steel, especially carbon steel, can occur quite rapidly, and it doesn't depend on the pH level of the sulfur, believe it or not. And you also have acidic corrosion when that happens when acid is present in the sulfur. Now, again, I'm not going to go too much into the detail of these corrosion processes. I've got plots and all that. But you have to control this by metallurgy and linings that are acid resistant. Then fires and explosion. Like I mentioned before, you can have static discharges. Typically, when you drop sulfur from a height in air, in dry air, or even liquid sulfur when it's flowing at a high velocity, say, for example, you're pumping into a pit or something like that, and there's a large drop, you can have static. And I've seen explosions in pits, fires in pits set off by the static discharge. If you are not careful, you have to make sure that, first of all, you design so that you don't have these drops, and all the equipment, anything dealing with sulfur, liquid or solid, you have to make sure it's all properly grounded, bonded, all that good stuff. Very important. I've seen major towers blow up where they've dropped sulfur through heights, both liquid and solid. Sometimes, even loading rail cars where they don't have chutes, telescoping chutes dropping down, and they drop from large heights, you can have fires or pops. Then there's also a class of black iron sulfide compounds that are sulfur deficient called mecanowite, that is Fe2S3. When sulfur contacts steel, especially carbon steel, when you in the absence of oxygen, these are typically found in sulfur tanks if you're not careful. and when your levels keep fluctuating, and when suddenly you expose it to oxygen, and if there's some moisture, these are pyrophoric. They'll just catch into fire. I've seen tank fires because of this. Even coils, heating coils, for example. If you're not careful and you see this black substance, you immediately wet it down completely so that you convert it to rust. A very interesting side note on this issue is you want tanks on the inside, sulfur tanks, they're typically carbon steel. You want them to rust. You want them to form iron oxide because it forms a passivating layer. One of our plants, the superintendent during his 20-year shutdown, went inside his tank to inspect it, and he saw the rust formation, scraped it all off. And guess what? For 3-4 months after that, he had nothing but fires. Another interesting thing is you do not sweep sulfur tanks. Typically, you do not sweep sulfur tanks with nitrogen because that allows these compounds to form. And then during maintenance shutdown periods, you can't help it. You shut off the nitrogen, oxygen comes in, and you catch fires. So typically, liquid sulfur tanks are swept with air. And then the other issue you're faced with is car soils. These are found when hydrocarbons are present in the liquid sulfur. And these typically happen when you have an upset in your Claus process, in your sulfur recovery process. Some hydrocarbons are carried over, things like carbon disulfide, carbonyl sulfide, stuff like that. And they can react with the sulfur. And you have these hard black compounds that will settle in pits. It'll settle on heating coils. That's why in remelting sulfur, you want to avoid as far as possible, if you're dealing with contaminated sulfur, any heating coils that are exposed to the liquid sulfur itself. You want to jacket it. You want to use other methods that we can discuss later on. Otherwise, what happens is they get coated and you lose the heating effect. And typically in pits, what happens, these compounds form, and even in tanks, this happens over a period of time. And that's why you have to shut down to do maintenance on tank. And when they drain the sulfur, you find a hard, thick black mass at the bottom that you have to jackhammer out, either in pits or in tanks. Then the other issue we have with these blocks are sand, silt, gravel, pine cones, needles, all the debris from the ground. I've seen, we are in the process of doing a remelt job in Alberta, and you won't believe the amount of gravel that's coming through that needs to be removed from the process. The most difficult thing here is dealing with silt. Silt is very fine and just does not settle out. And if you have an excessive amount of silt, even filtering, I've seen where you change your filters your big 4-foot diameter filters, you change every 2 hours, just not feasible. So the only option there is to use very expensive leaf filters where you have to use diatomaceous earth, and you have 12-hour operating cycles. Expensive operation if you have silt, if you have to remove silt from sulfur, but that's where the option of blending it with compost is a good option. And of course, the other issue, like I mentioned, is liquid sulfur has a very finite vapor pressure, and it will solidify in any cold spots. So all your instrumentation has to be specially designed and equipped to prevent this from occurring. So I'm talking of temperature gauges, pressure gauges, flow meters. What works in refinery service will not work in sulfur unless it's specially designed. Okay, so this is almost, in all my years, even though I have battled to get this has almost never happened. But this is crucial. And that's why I've seen a lot of remelt processes not work. Generally, you're dealing with pure sulfur. You're not dealing with most of the issues that I've pointed out, but I've seen every one of them. So before you start a melting process, these are the items that how you select your process. First of all, how much do you have to melt? I've melted blocks which are 660,000. That was a block up at Crossfield. Then a block up at high level was about 180,000 tons. Block up in northern Alberta was about 250,000 tons. So each one is different. If you have a large volume, then of course you want to do, you'll have to spend a lot of money, make sure you've got robust equipment. If you don't have a lot, you can get by with using less expensive stuff. You need to know what sort of throughput you want to put through. You want to melt at 500 tons a day, 1,000 tons a day. How long do you want to take to melt the block? The sulfur content of the block, its moisture content, again, all these sort of things, acidity, fine settling velocity, all these things you can do lab tests for, and will help you, will guide you in selecting your melting process. So we go to the melting processes. Here we go. There are basically three types. One is an in situ vertical remelter, and I'll show you a picture of that and explain it. Not in use anymore. Most common process is an in-ground pit, outfitted with heating coils. These can be either cast in place. This is where you, if you have a lot to be remelted, and it's going to be over a period of years, you want to build a proper pit with very thick walls. If it's a short one, if it's a year or 2 years, you can just put burn core blocks together. But of course, you have to be aware of the fact that there are things you have to do. And these have heating coils with typically serpentine. I'll show the picture in the next page. And then you have nowadays, you get above ground tanks, which are fitted with agitators and efficient heating systems. So I'll just briefly discuss it. I apologize for this picture if you can see it, but this is the in situ remelting process. So basically what it is you see this big rectangular thing, whatever it is, has heating coils at the end, vertical heating coils, serpentine heating coils. And what it does is it presses against the block and melts the sulfur. The sulfur runs down into a collection trough at the bottom, and then it's drained down into your collection tank, pit, whatever. This is what was used initially in the 80s and all that. The problem with this is you can see it has a lot of, it's very fumy around it, around the melting area. It has lots of emissions, and the steam coils corrode. Because they're typically carbon steel, you have to use very thick. I mean, you can't use, you can go schedule 80, but anything more, you don't have the heating efficiency. And just because it has been used, it has worked, but nowadays, because of the environment emissions and all that, it's fallen out of favor for quite some time now. This is the most common now. Is I don't have proper pictures of pits, so I had to take something off the internet. But basically, this is the pit, the gray area. It needs to be, thick concrete slabs. You have to be aware of water table issues and hydraulic pressure, as well as ingress of water into the sulfur. That can affect it quite a bit. So you can see these red, these are the heating coils, the serpentine heating coils, and has a concrete slab because, again, you don't want, I've seen pits which are open, working fine, but then you have issues with rain and snow and all that affecting the melting. These serpentine heating coils typically are in banks. So you have a bank of, say, 4 coils and another bank and another bank. And they are sloped. Actually, they're typically sloped with a sump at one end where you have the sulfur pump, so that when you want to drain the pit, you have to drain it below the heating coils. Otherwise, you just can't get the heating coils because the sulfur will solidify in the coils and be difficult to remove. So you have to have a sump which is lower than that, and make sure you drain everything below the heating coils, and then you remove the heating coils if there's a steam leak or any issues, or if you have to clean out the pit. Like I said, you have to jackhammer the castle that forms, and typically it happens every year, 2 years, depending on the quality of the sulfur. But this is what's the most commonly used right now. There are improvements now. This is an above ground sulfur melter where You use an agitator and jacket it. See here, you don't have any heating coils, which are right in the sulfur. You have a jacket around this vessel, and you have an agitator to make sure everything is agitating. Your solid sulfur comes in, and it goes into this pump tank here, where it's pumped through a heat exchanger and back into this. So what this does is you're providing the agitation, and through the heat exchanger, you're heating the sulfur and you're providing the heat. So this is an efficient way of heating. And then you pump out part of your throughput out of here. So this can be a fairly high recirculation rate, and you pump your throughput out. But this is suitable mainly for clean sulfur, because as you know, it drains through the bottom. And sometimes if you have stuff like gravel and so on and so forth, you can clog this up. Sometimes you can put a basket here to grab the gravel, but or the castle that forms. So that could be an issue if you drain it at the bottom, but you can use it for relatively clean sulfur. This is a new one for processing contaminated sulfur. Now, typically all the sulfur in all these processes, you have to feed at a very slow rate, a control rate. In the good old days, in these pits, typically what they do is the pits are open, they take front end loaders, bash into the pile, come and dump it into the pit. You have a big cloud of fumes, and these operators would just fill up the pit with solid sulfur and go sit in the control room, wait for 10 hours for it to thaw off, watch TV, do whatever they want. And the melting would take a long time. And we found we could speed up the melting by a very controlled, slow rate feed into the pit. And that's what this process makes use of. So this is the melting tank right here. And this opening here is where the sulfur is fed into. And it is a conical settling tank. So if you have gravel, so on and so forth, everything settles down to the bottom, and there is a continuously moving auger. So as opposed to the last process, this is a continuous removal of the sludge, of the sediment, of the gravel, whatever. And it goes into a pump tank that pumps the sulfur into this heat exchanger. It's a vertical shell and tube, so you have no issues with any plugging of the tubes or anything at a very high velocity. So typically we design this with, for example, for a throughput of something like 35 to 40 tons a day, 35 to 40 tons an hour, pumping out to the settling tanks, or to these filters first. These are the 4 filters that we use, wedge wire filters. We'd circulate at 450 tons an hour back into the thing, back into this unit. And we sock the steam to like 10 bar steam. Typically you melt at about 6 to 8 bar. We put 10 bar steam, and a very high flow rate gave us tremendous agitation, gave us all the melting we needed, and it worked quite well. You had continuous removal. This went into, if we needed, into another settling area which had an auger to remove the fines, or you could go through these wedge wire filter systems. That is one of the new ones that are operating right now. But again, these things are a little on the expensive side, and but work well. And it's been a little long, so come to the conclusions, basic and remelting. Again, these are the points. Your remelting has to be carefully planned at the start if you want to succeed. You have to understand your safety and environmental factors. For example, if you have any off gases, do they have to be scrubbed, or do you have to have a tall stack? That type of thing. And depends on the footprint. Sometimes you don't have a footprint, then you might have to go with above ground tanks, because pits typically, for say 1,000 ton a day operation, you need at least a 500 to 750 ton pit. So that's fairly long. You need about 30 to 20 meters, 30 meter by 20 meter rectangular pit. Of course, like I've hoped to bring it to you guys, that it's important very important to get a good analysis of feed sulfur for these conditions, and your local environmental regulations also determine the process to be employed, because with the allotropic melt, there's no way you can control the environmental issues. pit, you can, and the next two processes, for sure you can. You can vent the gases to a scrubber, to an incinerator, whatever. And that's it.
Oh,
It was a long one. Sorry, I hope I didn't give you too much or whatever.
okay. It was good, Jimmy. Thank you very much. Now, yeah, open to any questions anybody have. You can send in your questions, or you can
If anything
raise.
occurs to you guys, you can always email me with your questions. It's not an issue.
Um, Jimmy, I have one question. I may start off. I think in the 90s or so, when you drive up to Edmonton and near Crossfield, there's a mountain.
That is a block, yeah. That is a block, yeah. That's a block I was in.
Yeah.
I was melting.
There was some issue of the sulfur contaminating the soil, and the farmers were complaining and all that. Has that
Look,
been cleared? Do you know anything
okay,
on that?
that was one of the most difficult melt jobs I've done because of the proximity of Airdrie, the proximity of Crossfield, and the Muddy's mushroom plant, because they used to give off orders that we were blamed for. Believe it or not. Okay, but yes, that's what happened. Was like I said, it was an open pit that was first designed, and when I joined the company, they were using front end loaders to excavate the block and dump it into the pit, and you'd literally have a mushroom cloud of fumes and vapors and all that, and it would drift the sulfur into the plant, this fine sulfur into the plant. So in winter, you could see all this yellow stuff, you know, around the plant.
Okay.
So that's when we changed. We put in a grizzly. We put in a hopper with a 4-inch grizzly, so these guys couldn't dump large particles. They would backblade it into very sized particles, and we conveyed it very slowly and put a roof on, and vented the exhaust. That worked very well. We melted the block down to the base pad, and then base pad, you're allowed to leave a meter or so of the sulfur on there.
Okay.
By that time,
Yeah,
the sulfur prices, pardon me,
there are a couple of more questions, Jimmy.
I haven't finished. I haven't finished.
Oh,
And then what happened was, when we came down to the base pad, and at that time, sulfur prices spiked
yeah.
and to $770 a ton. And what we did was, we bagged the base pad, we bagged contaminated sulfur, bagged it and sent it to China at $450 a ton.
Oh,
Believe it or not. But we had a short window, so a lot of the contaminated sulfur went. Now, any sulfur that's left behind on the land, if you can't reclaim it or send it to landfill, it's typically limed. You typically lime the sulfur to neutralize it.
okay. There's another question. Who is it from?
Doesn't matter. Tell me the question.
Would you please provide some details about the instrumentation valve design in sulfur applications?
Yeah,
This
those are
is
details.
Kevin Zhang.
Yeah, I can do that. I mean, I have to go to our. They're all very specific instrumentation. If you give me a thing, I can send you what our typical instruments use, what are flow meters, what
Okay.
flow meters work best in sulfur services, what
Okay.
pressure gauges and temperatures and all that. I mean,
All right. There's another one from Richard. What are the main uses of sulfur, and is production generally larger than consumption?
the production larger than consumption, I can't answer. The sulfur moves for sure. That's a marketing issue. That's probably why you have these fluctuations. And I think the biggest consumer of sulfur, the sulfur is a precursor to the fertilizer industry. So it all depends on the fertilizer industry. If they are making fertilizers, buying fertilizers, people are buying fertilizers, sulfur will move. When there's a little jam in the fertilizer business, then it does it. Now, sulfur is also used as a fertilizer on its own, as sulfur, is what is it? Slow release fertilizer blended with the bentonite, which is an expanding clay, and it also has pharmaceutical uses. It is used for vulcanizing rubbers. There are other uses, but sulfuric acid is the main one. Others are all just small.
Okay. There's a question from Nigel. What happens in the prilling process to reduce friability and production of fines?
It depends on the prilling process. Again, it depends on process conditions. You've got air prilling, you've got wet prilling, you've got granulation, you've got rotiform. It's basically process parameters that control it. They are quite important, as well as gentle handling of the product. If the product is going to be dusty, then you have to bag it.
Mm-hmm.
But there are process parameters that I've spent my life on figuring out, on granulation especially. That's the one process I work on, granulation as well as wet prilling. There are several factors in the process that you can control to minimize your dust formation, as well as fines formation, as well as friability. And these days, the product you get is pretty good.
Okay.
Though there's not that, surprisingly, the best product is air prilling. The best for it's small, but the problem with air prilling is it has serious environmental issues, and the process itself was never used after the 1980s, when a couple of air prilling towers were installed in Saudi Arabia and they blew up. And after that, the air prilling tower has never been used, except the ones that were already installed. And we had one at Waterton. There's one up at I can't remember where, but they're pretty much being decommissioned, mainly because of environmental issues. There's one at Strachan, but that's been decommissioned. Wet drilling is safe environmentally, but the best product is right now in the market is the granulation product in terms of friability and dust generation.
Okay, there's a comment from Derek Brown. I'm sure you remember, Jimmy.
No, I don't remember, Derek.
Walsack gas plant was built for sulfur recovery. Hydrocarbons were byproduct. That's a comment from Derek.
Okay, yeah.
Um,
Yeah, we operated the Balzac plant for a long time.
Okay.
Jimmy, how many blocks are there now in Alberta? A lot of them have been
Almost all have been reclaimed. There's only that one major block, Terry.
I see.
And I think CNRL has a block too, but not a big block.
Not a big block. Okay.
The other one is a big one.
So,
And that they are looking at. Actually, I've been part of consulting for the company that's putting in one of the largest farming plants in North America up south of Fort McMurray. Well, it's not a secret. Kier Energy is doing it in partnership with Suncor, and I've been consulting on that. So they are planning to, actually, the shovel is in the ground, and they're going to be excavating the block at Sinkwu, and that's a big block. Excavating that block and sending it down to be remelted.
yeah. So is most of the sulfur that's being transported now being transported in liquid form?
Yeah. Pardon me?
Is most of the sulfur that's being transported, is most of it in liquid form now?
That's it.
Correct.
Right.
Correct.
And what about,
I wonder who the person is. That's what I'm wondering.
Okay, just a minute. Terry, are you done?
yeah, I'm done.
Okay, Ravin, go ahead. Did you want to say something, Ravin?
Hi, Robin.
Oh, his mic is muted. I see the mic is muted. Ravin's mic is muted.
But I think Hugh, is it all muted, or
I see that his mic is muted.
it came on?
Did it?
Yeah, I've tried to unmute him, but I'm not. He may need to unmute
chat,
as well.
maybe. Can you go and chat?
Thatchy, while you're waiting, it's Alan Murray. I had a question. Well, first of all, it was a really interesting presentation, and particularly at the beginning, Jimmy, when you were talking about the phase properties of
That's pure sulfur.
For
I did not mention one thing. Now that you raise the topic, is that from the Klaus process, the sulfur comes out from the condensers at about 190 degrees and it flows freely. The reason for that is because of the H2S content. If there's H2S in the liquid sulfur, the viscosity, it acts as a diluent and it will flow. So even if you have sulfur at say 165 or 170, if it has H2S in it, it'll flow freely. If you degas it at that temperature, you're asking for trouble.
Well, my comment really was that when that just looking at the contraction as it changes phase, because at Tumbler Ridge, a company was pumping liquid sulfur rather than move it by truck. They put it in a pipeline, and of course they had the heat wrap. They had electrical heating coils around it, which was fine until they had a thunderstorm and it knocked out the electrical power. And they thought they could drain the pipeline before they, before power could be resumed, but they weren't successful. And the liquid solidified, and like water, it expands.
No,
which was your point. Well, it bulged the pipe.
Yeah.
Because as you say, it was it contracts by what, 6 or 8% or something like that as it goes.
13%, yes.
Well, it sure made a big mess, because when it expanded, it burst the walls of the pipe. And because the pipe was insulated, you couldn't see where it had burst.
Correct. Very good point. Thanks for raising that. Like I said, there's a major 22-mile pipeline in the Middle East that burst for the very same reason too.
Yeah.
So typically, ideally, if you lose steam, you want to drain your sulfur.
Right.
If you can, drain it, or make sure you have uniform heating all the way through. That's why usually jacketed pipe is the gold standard. They've now come up with channel tubes like Contamination and all that, which are okay for pipes, small pipes. But on large pipes, because of the non-uniform heating, if you don't get good heating, if you lose steam, you're in trouble. Same thing with electrical heating. That pipeline that ruptured in the Middle East was electrical heating. So long as you it's designed to give you uniform heating,
right,
and all the way through, you're fine. If you don't, then exactly what will happen is what you raised.
Yeah. Thank you.
Thanks for that.
Okay, everyone. I think we have taken quite a long time.
My mistake. Sorry. I didn't know.
Thank you, Jimmy.
Hugh, go ahead, and what do you want to say?
Oh, Thatchy, I think we just wanted to thank Jimmy and just mention, were you going to mention the gift to Operation Eyesight?
No, go ahead.
Oh, okay. I'm not sure I have all the details, but Jimmy, what we normally do is as a thank you, rather than giving you a book or something like that, we make a donation on your or our behalf to Operation Eyesight.
Fantastic.
Yeah. Sorry.
What a wonderful idea.
Yeah.
Now, the gentleman who wanted information on instrumentation, he can email me, and with what specific instruments he's interested in, I can dig up the information for him.
Okay. Anyhow, thank you very much, Jimmy. I think we had a good number. About 20 people attended. There were a few cricketers as well.
Forced in, dragged in.
Yes. Thank you once again, Jimmy. And
thank you for the opportunity, guys. Thank you for the opportunity, Hugh.
Yeah, we certainly enjoyed it.
And if you need any more information on sulfur at a much later date, I'll be happy to. If you have anything in that area, I'd be happy to discuss if you ever want.
Okay. Is that okay, Hugh?
I will stop recording. Thank you very much, everybody, and we'll get you Kevin Zhang's email, Jimmy, very shortly.
Sure, sure.
Thank you.